Hello everyone. This is part 2 of inverse Laplace transforms and more, I called it. So we saw a bunch of examples with inverse Laplace transforms, and then we started talking about the and more part, which is special piecewise continuous functions. So we defined the unit step function here, and it was just a jump at t equaling 0 to 1, so it jumps up to 1. And its Laplace we had shown was equal to 1 over s. So now we want to consider the same situation, but we're going to define u sub a of t to be equal to u of t minus a, and that's going to be equal to, in a similar way, it's going to be 0, but now when t is less than a, and it's going to be 1 when t is greater than or equal to a. And so if we sketch this graph, it's basically, as mentioned, just a horizontal shift. So here's our t-axis, and it's going to jump up to 1, but at some value of a. So when it's less than a, the function's 0, and when it's greater than or equal to a, the function is 1. And so this is a graph of u of t minus a. And so we're interested in the Laplace transform of this. So let's say we want to find the Laplace transform of u sub a of t. And we're going to consider using our definition for the Laplace transform, the formal definition that we started with. The Laplace transform of a function f of t is equal to the integral from 0 to infinity of e to the negative st times the function f of t with respect to t. So using that formal definition, this becomes the integral from 0 to infinity of e to the negative st, and then the function is u sub a of t with respect to t. Now, because u sub a is 0 when t is less than a, any value less than a, the Laplace is 0. So therefore, if we replace u of a of t by 1, it's only good for values of t that are greater than or equal to a. So this limit of 0, when we replace u sub a of t by 1, the limit of 0 changes to a, because it's only defined to be equal to 1 when t is greater than or equal to a. So then we can integrate that. I guess if you wanted to show, get rid of the 1, just get e to the negative st. Then there's our rule for e to the kt. So 1 over negative s, or negative 1 over s, e to the negative st. Okay, we use that familiar shortcut notation from 0 to infinity, or not from 0, excuse me. Oh, I wrote all of that. I am so sorry. I wrote all of that without you being able to see it. I'll give you a second to catch up here. Okay, so just recapping the Laplace of u sub a of t. Okay, using our definition here, plug in u sub a of t for the f of t, and then we have, as I was arguing, when we replace u sub a of t by 1, this limit lower limit changes from 0 to a, because it's only defined to be 1 when t is greater than or equal to a. So I just recopied it, and then we integrated, and there's the familiar notation. Okay, so now limit as b tends toward infinity of negative 1 over s e to the negative st from a to b. So the limit as b goes to infinity of upper limit goes in, so negative 1 over s e to the negative sb, and then minus 1 over s e to the negative sa. But then as b goes to infinity, and s is long, provided that s is greater than 0, this term is going to tend towards 0, because then we'd have e to the negative infinity, as long as s is a positive value. So then we just get plus, we get the double negative, 1 over s times e to the negative sa. Okay, which typically will say that the Laplace then of u sub a of t is e to the negative sa over s. Okay, so now we're going to use that result, and we will, okay, so we're going to use that result to solve a particular problem. I'm not going to give you anything like this on the test, but this is a problem, one of the problems similar to one of the problems in the homework. So this is what we're out to look at, the unit staircase function. So this is what is defined by f of t equaling n, if n minus 1 is, if t is between n minus 1 and n, for all positive integers n. And so the first thing we'll do is sketch the function, and it looks like the name suggests, the unit staircase. That is, if we have our t-axis and it's basically saying, okay, first consider we're starting when n equals 1. So between 0, equal to 0, and less than 1. This should be strictly less than, sorry. So that should be strictly less than. Equal to 0 but not equal to 1, it's going to be the value of n, which is 1. So at 1 equal to 0 but now not equal to 1, in the t direction, it's equal to 1. But then from 1 to 2, so now the value of n is 2, so in this inequality notation, t is going to be greater than or equal to 1 and less than 2, strictly less than 2, the value of the function f of t, so if you want to label this as f of t, is going to be n, which is 2. So then at 2, it's equal to 1 at, or it's equal to 2 at t equaling 1, non-inclusive at t equaling 2. And then it steps up again. So now when n is 3, 2 is less than or equal to t, which is less than 3, are the t values, and the function is going to be 3. So closed on the left, open on the right. So you could obviously see why we call that the unit staircase function. So what we want to show here is something special. And we start by considering the right-hand side. If we look at the right-hand side, it's the sum as n goes from 0 to infinity of u of t minus n. Okay, and so for n equaling 1, well, actually, we have to start at n equaling 0, because this value of n is 1, but the left for t equaling 0, I should say, or no, when n equals 0, this would be u of t. When n is 1, so then summation operator, plus when n is 1, u of t minus 1. When n is 2, u of t minus 2, and so on. Now, recall that we defined on the previous page u sub a of t to be u of t minus a. So therefore, we can call this u sub 0 of t plus u sub 1 of t plus u sub 2 of t, and so on. And this is where u sub a of t, as we had defined it, is equal to 0 if t is less than a, and it's equal to 1 if t is greater than or equal to a. So now, if we add the right-hand side, so take this sum, what we get is, okay, I'm going to go down to the middle of this here, a little bit lower, because we're gonna show a sum. It's a big bracket. This will be the sum as n goes from 0 to infinity of u of t minus n. So the right-hand side, what we're looking at. So we're looking at summing these now. So when t is less than 0, then the function is 0, so therefore it's 0. But when t is between 0 and 1, equal to 0 but less than 1, we've got 0 plus this function would be equal to 1. Within that range. And so that's going to be 1. When t is between 0 and 2, now we're adding this piece, which is now equal to 1. So 0 plus 1 plus 1 would be 2. And similarly, when t is between, this would be, that's from 0 to 1, this would be from 1 to 2. So from 1 to 2, we're adding that next piece, and it's equal to 2. And then from 2 to 3, we're adding the third piece, u sub 3, which is another 1, so we get 3. And that continues. So therefore, we've shown that the sum as n goes from 0 to infinity, sorry again, okay, so recapping, when t was 0, it's going to be 0. When t is 1, it's going to be 0 plus 1. When t is 2, 0 plus 1 is 2. And when t is 3, add another 1, you get 3. and those would be the ranges. So we've basically shown that the left-hand side, or the right-hand side, u of t minus n is equal to n. If n minus 1 is less than or equal to t, which is less than n, for n equaling 1, 2, 3, and so on. And if you compare that to the original definition of the unit staircase function, back up here, f of t was equal to n, okay? So if, and then the same conditions, so if this is equal to n, and f of t is equal to n, then we've shown that f of t is the same as the sum as n goes from 0 to infinity of u of t minus n. Okay, so then the final thing is to show what the Laplace of this function is. So the Laplace of this function f of t, we could say is the Laplace of the sum as n goes from 0 to infinity of u of t minus n, which is the right-hand side of what we showed in part B. Well, as we were able to illustrate up here, that would be the Laplace of u sub 0 of t plus u sub 1 of t plus u sub 2 of t all the way out to infinity, of course. So then that would be, by the linearization principle, Laplace of each one separately. U sub 0 of t plus Laplace of u sub 1 of t plus Laplace of u sub 2 of t, and so on. And we know that u sub we know from the previous page that we had proven that the Laplace of u sub a of t is equal to e to the negative as over s. So therefore this becomes, okay, when a is 0, this is e to the 0, which is 1 over s. When a is 1, e to the negative 1s over s. So we've got 1 over s for Laplace of u sub 0, and then plus e to the negative 1s over s for the Laplace of u sub 1, and then plus e to the negative 2s over s when a is 2, so that's the Laplace of u sub 2. Let's slide one more in there. E to the negative 3 over s for for the Laplace of u sub 3 of t. And then there's something that we're going to do here that's a little bit tricky. Well, we're going to factor out 1 over s. That's not tricky. But for the first term, we'll just get 1. Here's the tricky part, though. We're going to write this, instead of e to the negative 1s, we're going to write it as e to the negative s to the first. Instead of e to the negative 2s, e to the negative s squared. And similarly, instead of e to the negative 3s, e to the negative s cubed. Now, the reason why we did that is because now we could say that this is equal to 1 over s times the sum as n goes from 0 to infinity of e to the negative s to the nth power. Because when n is 0, e to the negative s to the 0 is 1. When n is 1, we get this term. When n is 2, we get this term. And is 3, we get this term, and so on. And the reason why we did that is because now that's in the form of a geometric series. So you may recall that the sum as n goes from 0 to infinity of ar to the nth, where the absolute value of r is less than 1, converges to a sum, s, being a over 1 minus r. And the r in the formula that we're talking about, the absolute value of r, is the absolute value of e to the negative s, and that's going to be always less than 1 because s is greater than 0. So any value of s that you put in there, e to the negative s is always going to be less than 1. So therefore, in our sum, this r is e to the negative s. And the a is just simply equal to 1. So this would be 1 over s, and then times a over 1 minus r is this sum. So 1 over 1 minus e to the negative s. Or 1 over s times the quantity. 1 minus e to the negative s. Okay, so admittedly that's a little detailed and theoretical, but it's only a homework problem. So you can use this to model the homework problem that's very similar to this one, and I'm not going to test you on that concept, but obviously inverse Laplace transforms were important, and we're going to come back and we're going to see how to solve initial value problems using Laplace transforms.